welcome. In this video, I'm going to talk about image formation by lenses. This is really one of my favorite topics. Although there are equations, a large part of this is going to be visual. And I really enjoy the interplay between the pictures and the equations. I think it adds a lot to enjoying the topic, adds a lot to understanding the topic. We'll start with this equation called the thin lens equation. I mentioned earlier we assume the lenses are very thin, so that's all it means. We can assume that it's a thin lens. So what do we have? 1 over the object distance do plus 1 over the image distance di equals 1 over the focal length f. This equation allows you to place things, and I like to think of it as the location equation. Location of object, image, focal point. Now there's another equation that's very important we'll be using. This one right here. Capital M equals minus di over do. That's equal to hi over ho. This relates the distance of the image to the distance of the object to the size of the image hi to the size of the object ho. This is the magnification equation. The first equation deals with location. The second equation deals with magnification. We're going to be using pictures and equations. So if you need to pause the video, pause it, write down these two equations. I'm going to continue now with a discussion of how we relate the picture to the equation. We want to start by considering two situations. One, we consider what happens if the object is at infinity. Now, we're not going to worry about what it means to be infinitely far away. What we're concerned about is rays that arrive at the lens parallel. Because if something is very far away, the rays of light that come from that object will arrive at the lens parallel. We said in a previous video, when those parallel rays pass through a converging lens, they will converge at the focal point. That's the capital F. Then they diverge from that focal point. The fact that they diverge from that point is why you get an image there. It's similar to the object where the rays diverge. And that focal point is a distance f from the lens. How do I treat that with the equation? There is the equation on the right. If the object is at infinity, what would be do? Well, do would be infinity. So that's the symbol, that kind of sideways H symbol for infinity. How do we solve this equation? Well, what's 1 over infinity? It's 1 over an extremely large number. 1 over an extremely large number would be 0. So we're left with 1 over di equals 1 over f. We have to solve that equation. Well, the solution to that equation is simply that will be true if di equals f. So what does it mean? It means if the object is infinitely far away, it will form an image at a distance di f from the lens. That's exactly what we see in the picture. parallel rays, which would mean an object very far away, go through the lens, form an image of the point at the focal point, distance f from the lens. So di would equal f. Now let's consider another case. What about the object at the focal point? Well, now the picture would look like this. Notice at the focal point, that capital F, the rays are going in both directions. They're going to the right from the focal point because that's the object. Rays are diverging from that object. We don't care about the ones going to the right because we want to know what happens to the ones that go through the lens. So from the focal point, the ones going to the left go through the lens, they emerge parallel. Why? Remember the way the lens refracts light. You can solve Snell's law on the left side, Snell's law on the right side, n1 sine theta 1 equals n2 sine theta 2. And Snell's law doesn't care which way the ray is going, left to right, right to left. Same rays, same angle. So whether you go from the left to the right in the top picture, parallel, through the lens to the focal, or the lower picture from the focal to the lens, that emerge parallel, you'll see you would have the same set of angles on the right side of the lens, Snell's law. Same set of angles on the left side of the lens, Snell's law. It would work either way. How about the equation? Well, if the object is at the focal point, dO, the distance of the object from the lens, would be f. So I replace dO with f. Now, what's the solution to this equation? Well, in this case, I could subtract 1 over f from the left-hand side, subtract 1 over f from the right-hand side. I'd be left with 1 over di equals 0. What's the solution to that equation? Well, if 1 over di is 0, di must be a very large number. In other words, di equals infinity. What does it mean? Well, if the rays are leaving the lens and they're going to go all the way to infinity before they converge, when they leave that lens, they are going to be parallel. And whether they're, think of it as a limiting case. If those rays have to travel an extremely great distance before they intersect, they're going to be extremely close to being parallel when they leave that lens. So the equation which says di at infinity agrees with the picture that says the rays that are going to the left are going parallel from the lens. So these pictures and equations are important. They tell us a parallel ray striking a converging lens will go to the focal. A ray from the focal striking a converging lens will go out parallel. Now let's review the sign conventions for lenses. Object to lens, distance, dO. Positive before, negative after the lens. And it's defined at the below. Before means the side where the light comes from. After, lens, and side where the light goes to. Now, what it would mean that dO could be after the lens, we'll have to save that for another time. But the image you'll see very shortly in the video, it can be before the lens, negative di. After the lens, positive di. The focal for a converging lens is positive. The focal length is positive. For a diverging lens, negative. Remember, light can go either way through a lens. So all lenses have focal points on both sides. Okay. If you need to write this down, you can just stop the video, record it, and then continue. So we have two tracks, the equation track and the ray diagram track. Let's review the rules for the lens rays. Rule number 1. A ray arriving parallel will go to or from F. Now, a moment ago I said it would go to F. What do I mean from F? Well, you'll see there are different situations, converging lens, diverging lens, etc. Second case, a ray coming from or to F will leave parallel. Again, earlier I said a ray from F will go parallel. Now I'm saying to F. Well, we'll work through this case by case, and you'll see what this means. The third one is always pretty straightforward. Ray will pass straight through the center of the lens. So these rules may not be extremely clear right now, but if you need to, pause the video, write them down, have a copy in front of you, and as we go through the different cases, you can refer back to the rules to see how they apply. Here's the first situation we're going to solve. We have a converging lens. Notice, thicker in the middle. DO is greater than F. For DO to be greater than F, it means the object is further away from the lens than the focal point. You see it in the diagram. There's the object to the left, then you see the focal point, then you have the lens. Let's do the first ray. We're going to take the tip of the arrow. Rays go out in every direction, but we're going to select 3 of them that help us to find the image. So we start with a ray coming parallel. It strikes the lens. The first rule says, in the case of a converging lens, goes to the focal. So there you see the ray goes to the lens, goes to the focal on the other side of the lens. Now for the second ray, we said to or from the focal. How do we make a ray come to or from the focal? Well, we simply have a ray from the tip of the arrow go through the focal point. Therefore, when the ray arrives at the lens, you can say it came from the focal point. That's not where it started, but that's where it appears to come from. This ray coming from the focal will go through the lens and emerge parallel. Now at this point, you should look at the picture and realize we have 2 rays intersecting on the right. We're anticipating we're going to see a real inverted image. Notice we have not mentioned any numbers so far. It's just a picture, just a drawing. Therefore, we can conclude that any time that the object is further from the lens than the focal point, converging lens, we're going to get a real inverted image, because that's what this picture shows. Real inverted image. And the only thing we assumed was the object was further from the lens than the focal point. Now for the third ray. Ray strikes the center, goes straight through. Three rays intersect. They diverge from that. They converge to a point, diverge from the point. It's going to be an image of the tip of the arrow. If you do it for the whole arrow, you reconstruct the entire image, you get a real inverted image. That's the picture. Now we're going to say, how does this work with the equation? Well, notice at the top, there are some numbers. DO, 30 centimeter, F, 16 centimeter. If I was in the classroom, I'd use the whiteboard. So here is my whiteboard. DO greater than F. The case DO is 30 centimeter, F is 16 centimeter. There's my equation. I plug in the numbers for DO and F. Now notice I didn't do anything with the unit centimeter. Why? Because both of them have the same unit. If DO was meter and F was millimeter, well, I'd have to do some conversion to make them the same unit. But since they're already the same unit, I'm just putting the numbers in. But be warned, if you get a test question where you have meter and centimeter and millimeter, you have to use a common unit to solve the problem. Okay, so that one, if you plug that into your calculator, solution, DI, 34.3 centimeter. It's a positive number. It means it's after the lens. Since it's after the lens, when the image is formed, it's a real image. Now for the magnification. Minus DI over DO. So that will be minus 34.3 over 30 equal to minus 1.14. You can follow along with your calculator if you like. So this is equal to the ratio HI, the image size, to HO, the object size. Therefore, if HI over HO equals that number, I can conclude HI equals minus 1.14 HO. What do I conclude? Well, the negative sign from the number tells me the image is inverted. HI is negative relative to HO. 1.14 tells me HI a little larger than HO. That's what we learned from the numbers. And if you're going to go back to the diagram earlier in the video, you can compare. Now let's consider the meaning of the magnification. Here's a picture of an object to the left, converging lens, inverted image to the right. I can always draw rays that go through the center of the lens. So let's imagine one from the base of the arrow, one from the tip of the arrow. And I see how the rays from the object go and form the image. Now, what you see here is you have two similar triangles. Since they're similar triangles, we would say the horizontal sides, the ratio DI to DO, should be the same as the ratio of the vertical sides, HI to HO. That's the magnification. DI over DO, HI over HO. However, HO, DO, and DI are all positive numbers. To make the equation work, since HI is negative, we add a negative. Minus DI over DO equals HI over HO. Now let's consider the case. We have a converging lens Now the object is closer to the lens than the focal point. Let's see what this looks like. DO smaller than F, the focal length. Here's the parallel ray striking the lens. Okay, converging lens, that one will go to the focal point, similar to what we've seen before. But the second ray should come to or from the focal point. How can we make that happen? Well, the object is closer to the lens than the focal point. We have to make it appear that the ray came from the focal point. So we draw it at an angle. It's the same angle it would have coming from the tip if it came from the focal point. So you can consider from the focal point through the tip of the arrow up to the lens. So it's coming from the tip of the arrow, but it appears to come on a line from the focal point. Therefore, that will pass the lens, go out parallel. Notice we have not used any numbers, only a picture with the only assumption object closer to the lens than the focal point. You see those two rays, when they pass the lens, they're diverging. They're not going to form a real image. They do not diverge from a point. However, they appear to diverge from a point in front of the lens, before the lens. So that's going to be the beginning of seeing there's going to be a virtual image. Therefore, this diagram is going to be general. For any converging lens, DO smaller than F, you get a virtual image before the lens. The third ray, it comes from the tip of the arrow, strikes the center, goes straight through. Now notice what I've done with these rays. They go through the lens, but I've extrapolated all of them backwards. They all extrapolate backwards to a point before the lens. They don't diverge from that point. They appear to diverge from that point. Therefore, it is a virtual, non-inverted image. Okay, let's continue with the equation. Notice the numbers DO and F. DO is smaller than F. So there's the equation. We plug in the values for DO and F. Again, these are 30 both centimeter, so we don't have to convert unit. 1 over 17 plus 1 over DI equals 1 over 30. DI negative 39.2. It's a negative number. That means the image is before the lens. The rays are going through the lens. Therefore, if the image is before the lens, it's a virtual image where the rays appear to diverge from. That's the negative DI before the lens, virtual image. Magnification minus DI over DO. DI is negative, so that will be a plus 39.2 over 17. Magnification is a plus 2.31. We set that equal to HI over HO. Therefore, HI is plus 2.31 times HO. The plus sign means that HI is not inverted. It has the same orientation as HO. The 2.31 means that HI is, in this case, more than twice as big as HO. Go back to the picture that preceded this. HI is bigger than HO. Say, well, I wonder if that's useful. Yes, it is. That's how magnifying glass works. You look through it, you see something is not inverted, but it's bigger. Now, let's consider magnification of the virtual image. Here you can see in this picture the image is bigger than the object. Let's consider rays that come from the base past the center, from the tip past the center. Once again, you see two similar triangles. The horizontal sides will be in the same ratio as the vertical sides. Di to Do as Hi to Ho. However, Hi and Ho are both positive. Do is positive, Di is negative. To make the relationship work, it's minus Di over Do equals Hi over Ho. Okay, one more case. The diverging lens. You notice it's diverging, it's thinner in the middle. So we start with the rays. The parallel ray, because this is a diverging lens, it doesn't go to the focal after the lens. It appears to come from the focal point before the lens, like that. You notice I've extrapolated it backwards. The second ray is a little bit tricky. This ray is heading toward the focal on the right side of the lens. What will it do? We'll go through parallel. Why does it do that? How do we rationalize it? We use the logic we used previously. Imagine the light was going the other way. It was coming from the right side, heading toward the left side. That ray that I just drew would be a parallel ray going from right to left. It strikes the lens. As it passes through, coming out the left side of the lens, it will appear to come from, or appear to diverge from, the focal point on the right side of the lens. In other words, we use Snell's law on the right side of the lens, Snell's law on the left side of the lens. Same rays, same angles, and Snell's law does not care whether you're going from left to right or right to left. Just an equality you apply at each side. Therefore, since a parallel ray appears to come from the focal, if you reverse it, say a ray heading toward the focal, it goes through parallel. Now, well, let's do the third ray. Simple one. This one strikes the center, goes straight through. All three rays are diverging. They're not diverging from a point. They appear to diverge from a point because the point to the left of the lens where they appear to come from, those three rays are not all present at that point. They only appear to diverge from that point. Therefore, it's a virtual image before the lens. Now, notice we did not use the focal point on the left to make a ray go through it. we had one appear to come from it. We didn't make a ray go through it. Therefore, it doesn't matter whether the object or DO is greater than F or less than F. This picture can be used for any DO value where the object is before the lens. It will form a virtual image before the lens. There it is, a virtual non-inverted image. Now let's look at the math for the diverging lens. Notice we have a focal length minus 15 centimeter. Diverging lens, negative focal length. Let's place those values in the equation. We have 1 over 30 plus 1 over di, 1 over minus 15. The right-hand side of that equation is negative. So when we subtract 1 over do, assuming do is positive, we're always going to get a negative di. Solve the equation. I invite you to go ahead with your calculator, follow along. Di minus 10 centimeter. So minus means that it is before the lens. Since it is before the lens, it's going to be a virtual image. It's where rays appear to come from. Magnification minus di over do. Di is negative, so minus di. We get plus 10 over do 30 equal to a plus 0.333. That's equal to hi over ho. Therefore, hi is equal to plus 0.333 ho. The plus sign means this is non-inverted. Hi, ho have the same orientation. The 0.333 means, for this case, hi is about 1/3 the size of ho. Now you look at that, you say, okay, we worked a problem. We solve for di, we solve for hi, but what good or how useful would a lens be that makes things with a smaller image? You can see earlier I did a case where I said this would be a magnifying glass, larger image. But what about a lens to make something with a smaller image? Doesn't look very useful, does it? However, when we get to the subject of vision correction, you will find this is one of the most important lenses for vision correction. Now we've done some problems. We solve for di, we solve for m, but there are many other ways to state or frame these kind of problems. I could do a problem where you measure hi, you measure di, and if you know the focal length of the lens, you calculate, well, how far away is the image? I'm sorry, how far away is the object? You measure di and hi, if you have f, how far away is the object? Or you calculate how large is the object. So those kind of problems I hope to do in a later video. Before we finish this one, I want to mention, I already brought up the topic of vision correction. I want to mention the fact for vision correction, lenses are measured in diopters. What is a diopter? Diopter, also called the power of the lens, is 1 over the focal length of the lens, where the focal length is expressed in meters. If you have any kind of vision correction, whether eyeglasses or contact lenses or even reading glasses, those lenses are specified in diopter. So let's understand what that unit is. Suppose you went to an optometrist and you said, I want some reading glasses. You might be given a pair of reading glasses, or sold a pair of reading glasses that are 1.75 diopter. What does that number mean? Well, remember, here's my whiteboard. 1 over the focal length. Meters equals diopter, 1.75. So we invert that thing to solve it. We find, well, the focal length of that lens, 0.571 meter. Now, it's more common to express lenses in millimeter. So remember, 1 meter is 1,000 millimeters. Therefore, 0.571 meters would be 571 millimeter. If you go to optometrist, ophthalmologist, you get a prescription, you're not going to get a prescription. It says you have to go get a pair of glasses with a focal length 571 millimeter. No, you'll be given a prescription in diopters, like a 1.75. Okay, we'll come back to vision correction later, but for now I'm going to end this lecture, and I thank you once again for watching this video all the way to the end.